welcome to those of you joining us for this, which is the 9th in our series of webinars for 2015, which talks about the LimitState products with a focus on their features and their applications. For those of you who haven't attended one of our webinars before, my name is Tom Pritchard and I'm the host for today's session. I'll be introducing you to our speaker shortly and also presenting the second session and wrapping up at the end. Today's webinar is titled Assessment of Slabs in Buildings using LimitState SLAB, and it will provide you with an overview of how you can apply our new yield-line software LimitState SLAB to a wide range of building slab assessment problems. Our topics for today are an overview of yield line analysis, how it works and its benefits, automation of yield line analysis using discontinuity layout optimization, and then analysis of complex reinforced concrete slabs in buildings using the software LimitState SLAB. As always, the webinar is due to last about an hour and will include about 5 or 10 minutes at the end for questions, which you can post via the question functionality that's present in the webinar interface on your screens. We do try to answer as many of your questions as we can in the time available, but this isn't always possible, so we apologise in advance if we don't manage to get around to yours. But if you do have any questions that you would like us to answer, we try to get around to answering them all after the webinar for you via email. So without further delay, I'd like to welcome you to our first speaker today, who is Professor Matthew Gilbert, and he'll be speaking to you about the methodology of automating the yield line analysis, and I'll pass you over to him.
Thanks very much, Tom, and thanks very much to everyone for joining us today. Okay, so get straight down to business. Today's webinar is all about applying the automated yield line analysis method to existing buildings primarily, and the screen you can see now gives you an indication of the power of the new automated method. So what we have on the left hand side of the screen are a couple of failure mechanisms of the sort that you might see in textbooks, so relatively simple failure mechanisms. On the right are mechanisms which we'll be covering later in the webinar, which are clearly of much more complex geometries of the sort that you might commonly encounter in a building. And the key thing is that whereas with hand-based yield analysis, you would struggle to identify the mechanisms on the right, with the automated method you can clearly identify them. And here we can see now on screen that we can also automate the sort of animation of the mechanisms to aid visualization. Okay, just before we get into the webinar proper, just a few words about LimitState, the company. Company has been around since 2006. Key focus is on commercializing academic research, providing engineers with powerful software, primarily focused on analyzing and designing for the ultimate limit state. And what we're doing is what other companies are not doing, which is taking advantage of developments in optimization technology. And we are able to focus on ensuring the software is well validated, and perhaps that's a natural thing given our academic backgrounds, but also as a standalone company, we can focus also on supporting the software and making sure it's easy to use. Currently, the portfolio includes 3 main engineering analysis products: LimitState Ring for masonry arch bridge assessment, LimitState Geo for geotechnical analysis, and LimitState SLAB for concrete slab analysis. And the software tools are used widely in the UK and also in 30 countries or more worldwide. So just give you a quick screenshot of a page on the website which has a client list, and you can see we've got a selection of companies beginning with the letter A, but you can see that includes major names: ACOM, Amy, Arup, Atkins, and so forth, names that many of you will have heard of. Okay, so what's our motivation? Well, if you think of it from a sort of a big picture perspective, what we can say is that the fine element analysis has made So the finite element method has made linear elastic analysis very, very convenient and mainstream. So we can analyze structures, solids and structures of pretty much any geometry in a very reliable way now. The same can't be said for plastic analysis. So rigid plastic analysis tools, for example, are much less well developed, and many of those analysis methods have stayed on the pages of textbooks whose first edition was perhaps written in the 1960s or 70s. What do we mean by rigid plastic analysis or limit analysis? Well, it's a method used to directly estimate the maximum load that can be carried by a body or structure. So what we do basically is we ignore elastic deformations and we assume a rigid plastic material model. And that brings us some clear benefits when it comes to ultimate or collapse analysis. We can get there very quickly, but we can also get potentially more economical solutions when we're using it in a design context, and in an assessment context, which is the focus today, we can reveal hidden reserves of strength. If we look at the range of tools that are available to engineers to analyze the collapse or ultimate limit state, then what we can see is that they're divided into two real camps. The first camp I've coined traditional, which are basically based on hand analysis methods, and those methods may be actually performed by hand, or they may be embedded in a spreadsheet or in a simple program. And then at the other end of the spectrum, we have advanced tools based on, for example, finite elements, non-linear finite elements, discrete elements, and the like. And what we've observed is a major gap, a huge, large gap between those two types of tools. And we're attempting to fill that gap with what we regard as mainstream analysis tools, which retain much of the simplicity of the traditional tools, but allow much of the flexibility of the advanced analysis tools. So, for example, in the geotechnical context, we can analyze problems of arbitrary geometry with a variety of material models and so forth. Same applies for masonry structures, where we can get many of the benefits of both traditional and advanced tools. And today's session is clearly about slabs, and again, we're able to rapidly analyze structures of any geometry, something that you can't do with either traditional or advanced tools. Okay, so if we have a look at the traditional yield line method now, those of you not familiar with it, it's been around for almost a century now. The term yield line appears to have been coined by Slabs in the very first paper to have appeared in the Structural Engineer journal back in the 20s. But the real driver behind the method was Johansen in Denmark, and he developed a very comprehensive theory which underpinned the method. And it was later shown that the yield line method is essentially an upper bound plastic analysis method within the context of the plastic theorems which were developed in the 50s and 60s. How do you undertake a yield line analysis? Well, traditionally you might use a work method. So what you do is you postulate or guess a failure mechanism, you deform that mechanism by some small amount, and then you equate internal work done by the yield lines or along yield lines to the external work done by the applied load. It's a relatively simple process which certainly made it attractive in comparison to the elastic methods which were around in the sort of mid-late 20th century. So the advantages or the pros are that we get straight to the collapse load with relatively simple calculations. We get to economical designs or realistic assessments of capacity if we're dealing with an existing slab. The downsides, the cons, are that if you don't choose the right mechanism, then you will overestimate the true capacity. Another con is that it does simply look at flexural failure. So flexural failure is very often the driver behind the performance of a slab, but in some cases shear failure could occur, and obviously for service loads, then if you're looking at it from a design context, you will want to try to predict deflections to check that your finishes, etc., don't crack. So it isn't necessarily a full solution for slabs, but it is a very powerful solution. In the 1990s in the UK, there was a lot of sort of renewed interest in the yield line method, particularly in the context of bridges. And Middleton and co-workers at the University of Cambridge reassessed a number of bridges which had been identified using elastic methods as being substandard, i.e. weren't able to carry 40-ton vehicles. When plastic methods were used, using an automated yield line analysis tool, it was shown that the vast majority of those bridges did actually have the requisite capacity. So the key thing there is if you can demonstrate that a given structure has the capacity using the yield line method, then that can obviate the need for very expensive strengthening works. The downside of the method used by Middleton at that time was that it used a library of predefined failure mechanisms. So you can see that on the right there, a whole series of different failure mechanisms. The problem comes if you're dealing with a structure which perhaps has a slightly unusual geometry and a structure where one of these predefined yield line patterns or the critical one is not in that library. So you will end up with an overestimate of the true capacity of the structure. And in the context of buildings, which is the topic of interest today, that's potentially particularly an issue because very often we have a wide range of complex or irregular shapes in our buildings, more so probably than in the case of our bridges. So hand analysis or the use of a library of predefined mechanisms becomes problematic. And it's in this setting that automated yield line analysis really comes into its own, where we can potentially find hidden reserves of strength, and if that's the case, then potentially we can avoid very expensive strengthening works. So for example, you have a building where the client wants to put a multi-gym up on the 10th floor. The floor was never designed to carry those loads. The cost can be prohibitive if you upgrade it, but the yield line method may very well show that that slab is perfectly able to carry those additional loads anyway. The other key thing is that if you're dealing with an existing building, deflections can be checked in situ very readily. So effectively you can do a load test on your structure, and if the deflections are okay, then you don't really need to do any analysis. Predicting in-service deflections in concrete slabs is a non-trivial process, which fortunately isn't really an issue when it comes to the assessment of existing buildings, due to the fact that you can do a load test fairly readily. Okay, so what I'm going to do now is just open up the software, the LimitState slab software, and just show you it very, very briefly in action. I'll then explain how it works, and then my colleague Tom Pritchard will go through some more in-depth examples using the software. So what I'm going to do is just actually just going to freehand draw a slab just to show you the flexibility of the technique. So I've chosen a new empty project. I'm just going to click finish, and what I end up with is effectively a grid. I can change the size of this grid to suit my purposes, but I'm just going to use the default, and I'm just going to use the polygon control to actually draw a square slab with the corners cut off. So there's an example of a slab which is slightly different to ones which you might see in textbooks. I'm going to now I can change the boundaries, so for example to be fixed if I want, and alternatively I can select individual ones, and actually what I can do, for example, is make the opposite diagonal edges to be free. So now I've effectively got a fixed square slab with two of the corners sliced off. I can then apply a loading, so I can, for example, apply a pressure loading, and I'll just say that there's a unit pressure load applied to the whole slab for simplicity, and I can drag and drop slab properties as well. And what I'm going to do is just assume a simple unit MP passing moment of resistance value for the slab, which will allow me hopefully to actually solve the problem. And you can see there I've got now a predicted yield line mechanism. It's a relatively simple yield line mechanism, but it may take quite a long time to come to the same solution by hand. I can also animate the problem. As you can see exactly how that slab will deform in practice at collapse. So you can see that very, very quickly you can set up and solve problems which would have been exceedingly time-consuming to solve by hand, and that's really the key point with the automated method. We can do things that we simply couldn't do previously. Okay, so how do we do it? How do we automate the method? Well, we used something called discontinuity layout optimization. So it's a rapid and direct means of identifying the critical yield line pattern, and it's based on theory that was published in the Proceedings of the Royal Society. So it's a well-known science journal just last year. The way it works is that you discretize your slab with nodes. You then interconnect those nodes with potential discontinuities or yield lines in this particular case, and then you use linear optimization, which is a really simple problem to solve, to identify the critical yield line pattern, as you can see in the right there. In terms of the mathematics, what we're basically doing is we're minimizing energy. So we're actually minimizing the internal energy, but we're using the principle of virtual work to impose a unit displacement. So it's equivalent to equating internal and external work. And the key novelty, if you like, is that the main constraints in the equation are nodal compatibility constraints. And the way that works is, if you zoom in on a node, for example, the node in the bottom left corner of the slide shown here, what you need to do is actually traverse all the way around the node, resolving the rotations, or summing up the rotations in the x direction and the y direction, and making sure that those equate to 0. So what we're doing is making sure that the compatibility condition is enforced at each and every other node in the problem. And haven't got time to dwell on this in this particular presentation, but we also can show that at crossover points, that's at points where yield lines overlap or cross each other, this compatibility condition is also implicitly satisfied. So we have simple linear compatibility conditions which ensure that we have a geometrically compatible mechanism. And in terms of showing that it actually works in practice, because it's great to demonstrate the theory, but when you implement in software, you also need to make sure that the software is providing the right answers. We have done exhaustive testing of the software, and we, for example, for all problems where analytical solutions are available, find that we get very, very close estimates of those solutions. And a very simple example here is a square slab, which either has simple supports, fixed supports, or has a point load rather than a uniformly distributed load, as in the case of the right-hand one. And we actually get the exact solution for the left-hand slab. We get within 0.01% of the solution for the central slab, so that's a uniformly distributed load with fixed support, and we get a similar solution for the right-hand slab where we have a point load. And the key thing, sort of key differentiator compared with hand analysis, is that corner levers or corner fans are identified naturally. So there's no need to make assumptions and then apply a global factor of, for example, 10% to take account of inaccuracies in your method. We can get to within a fraction of 1% very, very quickly and easily with this method. A slightly more complex problem of the sort you might see in a building. Here we've got a variety of support conditions and also a hole, and you can see that we get quite a complex yield line pattern in this case. Difficult to identify this mechanism by hand, certainly, and we find that we can predict more accurately the true load carrying capacity of this slab more accurately than any other method that we've found in the literature. Moving on to a real-life example. This is an apartment block in London, and I don't know if you can see from the facade, but it has quite a complex external facade in terms of geometry. And actually, this particular building was designed, or the slabs in it were designed using the yield line method, but there were a large number of potential failure mechanisms that need to be considered, and it was a very time-consuming process to do that, and it would require a certain amount of expertise, particularly given this particular building was supported entirely on blade columns. So there's a wide number of potential failure mechanisms that could be critical. But with the automated method embedded in LimitState SLAB, it's really simply a matter of getting the geometry into the software, making sure you've defined the plastic moment of resistance for all the areas, and applying the pressure alert, and automatically within a matter of a few seconds you will get the critical failure mechanism. In this particular case, we actually found that the hand design was within 10% of the solution we got here, but in many other cases we find much bigger differences. Okay, so I'm going to now hand over to back to Tom Pritchard, who's going to talk you through the setting up and solving of a number of building slab examples.
Thank you, Matthew. So as Matthew says, I'm going to talk you through just setting up and solving a number of different building slab examples, just working up from something that's quite simple but shows you the different types of things that you can put into your problem, up to a more complex sort of real-life building slab example. So I think first of all, it's actually, Matthew's introduced you to it briefly, but just useful to see what is in the LimitState slab interface. So you can see at the top is the usual array of different sort of buttons, the ones in the middle being ones for loading, and then the ones on the right being to show and hide things. The most important parts, I would say, are on the left here, the slab definitions, which basically allow you to define different material properties for each section of your slab, and you apply them individually. So you put new NP values and unit weights and slab thicknesses there, and we call that a slab definition. And then on the right hand side we have a property editor where if you click on anything within the problem, so here I've clicked on the central solid, you can see that the properties of that solid are then displayed on the right hand side here, including the nodal spacing and also the material properties or the slab definition properties. Similarly, you can click on things like the external boundaries and see what type of support it has. So what I'll do is first go through a very simple problem, and what we've got in the software is a new project dialog which allows you to choose from a couple of sort of quick start wizards which allow you to then define a slab with all the things that you need to be able to solve it very quickly, and then the theory being that you can then go away afterwards and modify it to fit your particular needs. So it's quite flexible and it's quite easy to add things to the model to actually define the problem as it is. So if we start here, we've got a rectangular slab, and you can see the first tab here is basically just general information about it, so we'll just skip over that. The next one is the geometry, and we can see here we've got the dimensions, width, height, and also you can add a skew to it. And on the right hand side you can add support types, and what I'm going to do here is actually add simple supports all the way around our slab. So we're going to have a 5x4 meter slab with simple supports all the way around. Next up we've got the slab definition, and what I want to do is create a new one. I'm going to call it slab definition 1 and choose a color that allows us to identify it in the slab definition explorer. And you can see on the right hand side here are the properties. We've got MPs for sagging and also for hogging, and an angle which is defining the angle which is perpendicular to the line of the reinforcement. So example, if you've got a rebar at a 15-degree skew, then the angle of the MP will be at 90 degrees to that, so you would enter an angle of 105. For the moment what we'll do is just leave it as unity and 90 degrees to each other. Similarly, you can add a thickness and a unit weight, which will then, if you are taking into account the self weight of the slab, they will be used to calculate that. Next up we have the loads, and it's worth taking a little bit of time here just to explain how load cases work. So a load case in LimitState slab is a combination of an applied load and also a partial factor set, and you can see here at the top we've got load case 1. Here is our partial factor set, which at the moment is set to unity, but you can also define your own, and if I click on the details button you'll see that the thing is couched in permanent, variable and accidental terms. You can also have a factor on your material as well, factor on MP, but in this case everything is 1. So we have a partial factor set, and then we also have some loading applied, and you can see here already, because we're using the wizard, that a pressure loading, a unit pressure loading has been applied to our slab solid. You can see there that's the red lines around the outside of it. You can also define your own loads by going into the loads database and clicking add. You can have pressure loads, line loads and point loads, and then you can use these to build up loading patterns and different load cases that you then apply to your problem. And then when you click solve it, the software will go through all of them in turn and determine which out of the different load cases is the critical case and give you the results for that. But in this case, we're just going to look at this single one with a unit pressure load and unit partial safety factors. So if I click next, we'll go on to the analysis, and you can see here that we're looking at a nodal density which we've called medium. We've got a selection between sort of coarse, medium, fine, very fine, and also custom if you really want to put your own number of nodes in. But the target number here for a medium is 500. We'd say that's sort of very good for sort of scoping out problems, and that will determine the accuracy of the solution as you solve it. So the more nodes you have in, the more potential yield lines there are, and therefore the greater the scope for finding slightly more critical failure mechanisms. So if I click finish, you see here we've got some quick tips which we won't look at, and then I click solve. And you can see the software goes through a number of different potential yield line patterns until it settles on the critical one here. And at the bottom, we can see that the solution is saying that we've got an adequacy factor of 1.22. So that's basically saying that we can multiply up the pressure load on the slab by a factor of 1.22, and this would be the collapse mechanism that would then occur. And as Matthew was showing previously, you can then just query the collapse mechanism by rotating it and animating it and getting a good idea of how that problem would then fail. Similarly, another thing that you may be interested in is having a report of exactly what has been conducted in the analysis. So if you click on the report button, you can see here we've got critical load case and a number of different sections, and if I click OK, you can see that the software then generates a report with the important information at the top, so the adequacy factor and the failure mechanism shown right near the top, and then all the different problem parameters underneath it. And that can be saved as a PDF and obviously given to clients, etc. But this is quite a simple slab, so what we're looking at is sort of assessment of more complex building slabs. So things that we might want to be thinking about looking at are perhaps making the material orthotropic. So if I change the values here, so we'll put, instead of having MP in the first direction of 1, we'll change that to 5, leave the second direction, which is at 90 degrees, at 1, and see what effect that has on the problem. You can see here you get a similar envelope failure mechanism, but the horizontal portion of that failure mechanism is quite a lot more elongated than it was in the first case. And if we look at the adequacy factor, we had 1.22 previously, now we're at sort of 3.76, so nearly 3 times as much by increasing the MP value in that direction and having an orthotropic slab definition. If I go back to having it isotropic, so change them back to 1. Other things you might be interested in are potentially adding a column, which you could do quite easily, and I'm going to do this. So you can see I'll just put the grid on, and I can add a point here, which will be 2.2, 1.9, the second point of the column, which is 2.4, 2.1. And you can see here the little square has been made in the center of the slab, and to make that into a column, all we do is delete the inside of it, select the boundaries, and make them fixed. And you can see now they've got the crosshatch around it. Solve again, and instead of having the envelope failure mechanism, what we've got now is a combination of having an envelope but then with a fan around the column, and it's quite a complex mechanism for what is essentially rather a simple slab problem still. So you can see how you may be able to sort of benefit from using the software rather than having to conduct the analysis by hand. Again, the solution is about 2.5 times higher than the solution that we got for the same problem without the column in the center. So you can see very quickly what the effects of having that column are there. Other things you might want to do is change boundary conditions. So if I select the right hand side and make that free, solve again, we've got a a markedly different collapse mechanism from the ones that we've seen previously. So instead of having an envelope or a combination of the envelope and the fan, now we've got this collapse of the right hand side here, and we can animate it just to see what happens. And in this case, with the removal of the support on that right hand side, the adequacy factor is reduced back down to 1.5, which is slightly higher than it was for the initial case where we had support all around but no column. Another thing you might want to do is model the presence of an external column, and you can do that just as simply as you did with the initial one. So if we make that column at the right hand side and solve, then you can see again we've got a different failure mechanism that would be difficult to determine easily by hand, and the adequacy factor has again gone up. But as Matthew alluded to, one of the things that the software is good for is looking at the assessment of buildings when you're repurposing them. So for instance, if we wanted to model a patch load or something on this problem here, what we can do is go into our load case manager and then into the loads database and add a pressure load, which I might call gymnasium. Oops, sorry. And instead of it being unit, let's call it 5 kilonewtons per meter squared, and we'll make it a permanent load. Then all we need to do is define whereabouts on our slab we want to apply it. So I'm going to say on this rectangle here, I want to apply gymnasium pressure load, and I need to change and select that solid. You can see we've got S15 now has the gymnasium loading. What I'm going to do also is change it so that that section doesn't have the unit pressure loading. And again, all we need to do then is solve the problem. And you can see that the failure mechanism is much more concentrated around where that patch loading is applied. So you can see the thickness of the yield lines is an indication of the rotation that is being undergone at that area. So you can see there where the gymnasium pressure loading is, the failure mechanism is much more marked. So that's a very simple problem that we've looked at with a rectangular sort of cross section. One thing you might want to do is potentially look at making a geometry from scratch rather than using the wizards. So I won't save that. So you can also create an empty problem. And all that happens here is that you get the options for the grid intervals and the snap. So there's no actual definition of material properties or a geometry or anything like that. It's simply just saying what are the drawing settings. So if we click finish, you can see here that we've got a problem that's blank but with a grid that's already set up, and I'm going to make quite an extreme case, but just to show the type of problems that you could put in. Obviously normal building slabs maybe slightly different. So we've got a cross-shaped polygon. If I then select all the external boundaries and make them simple, the next thing we need to do is then add some sort of material to it. So I'm going to add unit NP concrete to it, and then add a load. So in this case we'll have a pressure load to start with, and we're going to use the existing unit pressure load and apply it to the middle there. So very quickly we've got all the things that we need to be able to solve this problem. We've got a geometry, we've got a material or a slab definition, and we've also got this loading on it. So if I solve now, you can see the type of failure mechanism that occurs there. So we've got sagging right in the center. Again, what we might want to do is see what effect having columns has on it, so we can add them very easily around the corners here. So if I delete those, then make all those boundaries fixed. We've got 4 columns, we can see what the difference in failure mechanism is. So we've gone from having an adequacy factor of about 11 up to having an adequacy factor of about 15. So maybe a 50% increase in the capacity there. But what if we have a point load, say, at the middle of this slab? Then all we need to do is, as we did previously in the previous example, is to then go into our loads database and then add a point load, and I'm going to call it column for the want of a better name, and make it 15 kilonewtons. And then all we need to do is add column point load at a particular point, and if I make it right in the center and then solve, you can see now that we've got this fan failure mechanism around that point load rather than having the sort of entire collapse of the whole problem. And we can very easily, if we want to, just change things in there. So that's an example of just making a very quick problem from scratch. The next one we're going to look at is more realistic, and that's the complex geometry of an apartment block. So one of the good things about LimitState Slab is the ability for sort of quite complex geometries is to import geometries from a DXF file that you may already have a drawing. So if I click that, you can see I've imported this. There's seeing which layers exist in the drawing, so you can choose which ones you want to add and which ones you don't. If I click OK, you can see here that our apartment block floor slab has been imported. And actually the problem is one a little akin to the example where Matthew was showing you from the Kennedy and Goodchild example book, where there aren't actually any external wall supports. It's all the whole slabs is being supported on internal columns. So what we can do, we can see that our geometry has been imported, and any of the closed loops in the DXF has been made into a solid for us. It saves us some time, and all we need to do then is go through and where our columns are, select and delete. So there's a few more there, but I can do that. So now for each of those columns, we've actually got a hole. So if we select them using the rectangle select, we can see that we've got external boundaries here. If I select them, make them fixed, then the software will assign, or we've missed one, the software will assign a fixed boundary to around all of those columns. So we've done that. The next step is then to generate your own materials for it. So if we make a new slab definition in the Slab Definition Explorer, we get this dialog box here, and we can call it what we want. So some of the things in the apartment block may be a kitchen, and we choose a color for it. So I'm going to choose a yellow. And again, if we want an orthotropic or an isotropic slab, we can input the properties here. In the first direction, we could say maybe 15 kilonewton meters per meter, and in the second direction similarly. So if we've got an isotropic slab, Again, as I mentioned previously, the thickness and the unit weight come into play if you are considering the self-weight of the slab as part of your analysis. So if I click OK, you can see that we've got a kitchen load there, and maybe that's our kitchen. We can apply by dragging and dropping the slab definition onto it there. And for a problem like this, you may have 4 or 5 different areas where you've got different types of usage of that area. So you define different types of slab definition and also different types of loading, which is what we're going to look at now. So again, we come to the load case manager, and in the loads database we've got all the different pressure loads. So you can add one, we'll call that kitchen, and you put in whatever the appropriate values is, so maybe 4.5 kilonewtons per meter squared for a kitchen. We could have bathroom, which is maybe slightly less, 3.2, and so on. And then once you define those in the loads database, they then become available for you to use within the project. So we can select the kitchen pressure load. For the position, we just change select where we've applied our kitchen slab definition, click OK. And we can see now if we turn on the display of loading, in that area there we've got everything we need. So we've got the geometry of it, we've got the kitchen slab definition, and we've also got the kitchen loading. I'm not going to go through everything with you quite now, but you can see how you can quickly build up your model. So what I'm going to do is actually just open a completed model. We don't want to save this one. So here's our apartment block. We can see we've got the balconies at the edges, the main floor slab, 2 bathrooms, 2 kitchens, and a stairwell, which depending on which particular design codes of practice, analysis codes of practice you're looking at, you can take as having the same properties as the rest of the slab. And if we click on maybe the kitchen slab definition here, you can see on the right hand side we've got MPs of 20 in each direction. And then if I look in the load case manager, you can see here that we've got all the different pressure loads applied, so kitchen, toilet, stairs and main. We look in the loads database and the values there are set as appropriate. So we go on and solve, and we can see in this case here the adequacy factor on the applied loading, and bearing in mind this is taken from a real example, we can see that the loading can be multiplied by a factor of 2.3 in this case, above the design value. So you can see that the slab actually has quite a lot of spare capacity within it to hold a different load. So maybe what somebody might want to do in there is add a gym. So maybe what we could do is in the loads database we can add another pressure load, which is gymnasium, make that 20 kilopascal pressure loading, and then apply that to one of the zones within our project. So maybe this end slab here wants to be the gymnasium, so that's solid 152. We go in there, just make sure that it's not in the main loading, so take it out of that. And then solve and see what happens. And as you can see now, the value has reduced down to 1.123, whereas before it was 2.3. But if you're happy with the partial factor sets that have been applied, you can see that still the floor slab in that area is capable of withstanding the gymnasium load that you might want to apply in that area. Similarly, if we unlock, we might just want to put a point load somewhere. So I'm going to put one right in the middle of the slab there, and if we create a new one and make it quite a high point load, you might want to see what the difference between having that there and the gymnasium, which is the most critical. So we click OK. solve and see what happens. And again, still the gymnasium loading is critical. So that's given you a very quick flavour of how you can put in a geometry and material properties, etc. for an existing building slab and see what happens when you maybe change the usage of it, and you can use it to easily determine whether or not you can take this extra load or not. So that brings us on, if I bring up the PowerPoint, to our conclusions. So what we've seen today is, firstly, the yield line method does provide a powerful means of analysing the ultimate, which is the collapse limit state, but a lack of general implementation has resulted in limited usage in practice, certainly in recent years, with finite elements, etc., perhaps being favoured over it. But with the implementation of automated yield line analysis via the discontinuity layout optimization method that we've developed, we can now make that available to people. So it involves a linear optimization, which is easy to solve, and it allows you to identify fan-type mechanisms as well as other more complex yield line patterns automatically, rather than having to go through and postulate potential patterns as you would have done by hand previously. For those of you who are interested, the software can be downloaded from our website, which is www.LimitState.com. And if you have obviously any questions when you're using it, then do get in contact with us. So what I'll do is pass you back over to Matthew now, and we'll see if we have any questions.
Thanks, Tom. Just looking at the list of questions. Okay. Okay, there's no questions yet, so don't be shy. Please fire away with questions. Okay, question is, how do we tackle problems where we've got varying slab thicknesses? So we have a building where we've got a slab thickness of, I don't know, 150 in one part of the building and 250 in another. Basically, that's relatively easy to do. So, for example, what we can do is we can select a given region. So I can select the region that I've highlighted, and I just simply assign different properties. So I can define a new slab definition, and I can assign the relevant thickness. So let's say 0.25 and the relevant plastic moments of resistance, whatever that might be. I'll just give it some arbitrary values in for now. And I can change the colour, make it some different colour to stand out, perhaps a bright red colour. Okay, and then I can just simply drag and drop that to the relevant area. Okay, so got an email from one of you. I'll just see if I can access that. Okay, shear can be a critical load case. So as I mentioned earlier on, the yield line method deals with flexural failure, not shear. Shear is sometimes an issue, but many times it's not. There are standard ways of dealing with shear which you can apply in conjunction with the yield line method. It may be something that we include in a later version of the software, but it's at the moment it's very clearly treating the yield line method rather than sort of muddying the waters with, for example, shear or serviceability deflections. Bending capacity is dependent on the type and orientation of the bars in the slab. Well, certainly you can change that. So we have, if you look in the property editor, or if I define a new material, you can certainly model orthotropic and also slabs with skew reinforcement. So you can change the orientation of the reinforcement in the slab. So it doesn't need to be 0 to 90, it could be 0 and 75, for example. So there's effectively two reinforcement directions that you can assign, and you can assign hogging and sagging moment capacities for each of those. Another question, will load testing be needed wherever there are different circumstances to verify deflections okay? Well, in a sense, that's something for you as an engineer to assess is how many scenarios you think would be sensible to try out in terms of load testing. But certainly from discussing this with our customers, they feel that the use of a relatively limited amount of load testing plus application of the automated yield line method gives them the assurance that they need to verify that, for example, an existing slab is okay, for example, to house their multi-gym on the 8th floor or whatever it might be. And then the last question in the email relates to calculating the MP value. So this is these will be calculated in exactly the same way as you calculate the MP values when you're doing the hand-based yield line method. So you simply analyze a section. You know what the reinforcement depth is, hopefully, either from drawings or from other investigations of your existing slab, and you can work out what a suitable plastic moment of resistance value is. So that's a fairly standard thing to do if anybody has dealt with the traditional hand-based yield line method, and it's available in any textbook on the subject. And there's a similar message, probably the final one before we wrap up. Are MP values provided by manufacturers? So reinforced concrete isn't really something that manufacturers would deal with, because we've got rebar manufacturers, and we've also got clearly concrete, which is a material separate and distinct from the reinforcement. So it's the combined action of those two things which gives us the plastic moment of resistance. So it's a standard operation to calculate the MP value. Okay, I think that's dealt with most of the questions that we've got. If there are any other questions, please do fire them to us. I'll just hand back now to Tom to wrap up the webinar.
Thank you, Matthew, and thanks to everybody for attending today. We hope that you found the webinar informative, and as mentioned at the start, if the presentation has raised any questions that we haven't answered at the end here, do just please get in touch via telephone or via info@limitstate.com, and we'll be more than happy to answer your questions for you. As I mentioned briefly, LimitState Slab is available to download or purchase now from our website, which again is www.limitstate.com, and we'll also be in touch over the next few days with everyone just to get some feedback on the presentation and find out if you have any further questions and see whether you think the software might be useful for you. If you'd like to watch the webinar again, or if you think you might know somebody else who would be interested to see it, there'll be a recording available hopefully later on today or tomorrow morning. We will email you with a link once it's actually there online. Also, we have a YouTube channel where all of the webinar videos are available to view, which is youtube.com/LimitState software. And finally, please do look out for the other webinars that we deal with LimitState, SLAB and our other software products, which will be happening over the rest of the year. We'll be sending out event notifications via email in advance of these, and they're also posted on our website at limitState.com/webinars. Finally, I'd like to say thank you all for listening, and I hope you can join us again for one of our future sessions. Goodbye.